The objective of this challenge was to find a way to generate voltage without using magnets. The voltage had to be enough to turn on a LED. What we did was an electrochemical cell, also known as galvanic cell, which consists in the following. We made cells with positive and negative charges. The positives are called cathodes and the negatives are called anodes. The positives are made with copper submerged in copper sulfate and the anodes with magnesium submerged in magnesium sulfate. Each positive side was connected with a wire to the next negative side, making our first cell the exit for our positive side and the last cell the exit for our negative side. Each cell was connected with a silane bridge, which has the purpose to permit the transfer of electrons between the positive and the negative cells. This transfer is the current that provokes the voltage to turn on the LED.
In this part, we changed the LED in order to check if that was the mistake, because we probably needed a little bit less charge, and the reaction generated a small amount of voltage. We also needed to change the liquids, which were the copper sulfate and the sodium chloride. And then we were checking with the multimeter if we were generating any charge. In this part, we can observe how we have to dip the silane bridges in sodium chloride in order to get them to transfer the electrons from both the liquids that we had that were also sodium chloride and a copper sulfate. And we generated the bonding bridges by wiring copper and a sheet of aluminum together.
In the first attempt, we failed because we didn't sand the materials correctly, and the solution ionized. So the electrons may not pass. So we need to start from zero, and we need to make new solutions. Clean all the stuff, because in the first attempt we didn't generate voltage, so the LED didn't bring up light.
In this part, we can observe how we're sanding the materials and also the metals and cleaning them up from the liquids in order for the charge to not ionize. When a charge ionizes, this means that the molecule or the atom is losing or gaining electrons. In this case, it already lost electrons because it was for too long inside the sodium chloride and the copper sulfate.
Understanding the behavior of a battery and understanding the way electricity is generated in a time where everything needs battery and electricity in order for it to work is vital for us. Also, because in a time when we understand how precious the environment is and how harmful batteries can be, given that they will release certain liquids and gases to the atmosphere and destroy it slowly but certainly. It's very important for us to understand in order to develop new ways to generate electricity.
At the end, we learned a lot by doing this experiment, especially about conventional batteries and the way they can generate enough voltage even to turn on a LED. It is important to remember that when we put together the cables and the LED, they must always be in the right position. Otherwise, the experiment won't generate voltage and the LED won't turn on. This is because the positive ions migrate to the negative electrode and gain electrons, and on the other hand, the negative ions migrate to the positive electrode and lose electrons. This movement of ions helps us generate voltage and in this case, accomplish our objective.
In our final attempt, we can see how we're plugging in the LED with the wires, and it apparently doesn't seem to be working because the cathode and the anode are in the opposite sides. Then we switch the LED to see if this works, and apparently it does by lighting up the LED in a very small amount in proportion due to the voltage produced. It was about 1.5 to 2 volts that we're producing in this part. But at the end, we finally came to the result we were looking for.
The objective of this challenge was fulfilled. We as a team found out a way to create voltage using a redox reaction. We generated enough voltage to turn on a LED, and we learned about the environmental consequences that conventional batteries have.